Good morning, superhumans. Welcome to another Sunday morning. At least I hope it's a good Sunday morning for everybody. And I'm running through StreamYard at the moment, so I would really appreciate it if I could get confirmation that audio is coming through. I've got no feedback on audio levels or anything like that. I've just got to trust that it's working. So today we have a special guest coming on the show. We have Tisham Dhar, who is the founder of the Watnik open source energy monitoring project. Oh, thank you, 50 Hertz and Aaron and everybody for the confirmation. And open source, well, energy monitoring is one of those topics that a lot of people that are into home automation are really interested in. And Tish has done some very cool work. So I'm going to add Tish to the stream. And hey, good morning, Tish.
Morning.
Hey, so you've been doing some really interesting things, and in January this year at linux.conf.au we had the Open Hardware mini conference, and you were kind enough to come along and do a talk about your Watnik open source energy monitoring project, which was really interesting. So ever since then I've been thinking it would be really cool to talk to you about it and maybe let people ask you some questions and things. But before we get into that, I just wanted to ask you a little bit about yourself and the sort of work that you do. So can you give a little bit of background on what your job is and what your expertise is?
Sure. Expertise is hard. Like in the LinuxConf, they also talk about expertise and how much we trust those things. Sometimes non-experts do good things because you're not blinded by your expertise. But my expertise is sort of remote sensing. So I work for the Australian government. I do DevOps, site reliability engineering, keep things running for a program in the Geoscience Australia called Digital Earth Australia. So there is a lot of open access satellite imagery out there from NASA, JAXA, ESA, and then it's sort of locked down to scientists. The mission of Digital Earth Australia is to sort of collect all that and then make it available to a wider audience, sort of on a near real-time daily streams, calibrate it with atmospheric corrections and so on, and make it science ready. And that sort of comes a bit at a slower pace. So I work in a site reliability engineering team there. So if people who do SRE, it means containers and Kubernetes clusters and cloud providers. And yeah, they recently made me assistant director. So I manage a small team.
Well, congratulations.
Thanks.
That sounds like a fascinating area to be in, not just in terms of the work that you're doing with infrastructure, but also with the type of content that you're dealing with. So the all of the content that you're providing for Earth Sciences purposes, can you talk about the sorts of things that's used for? Is it things like weather modeling, or what cool things are being done with it?
Yeah, a lot of different things. One of the premier products, I think, is water observations from space.
Mm-hmm.
So it takes the backscatter data and then sort of the reflectance data, calibrated. Everything is sort of normalized for all of the atmospheric changes and lighting condition and terrain differences. And then you can build these machine learning models where you can say this area is water or not. And a lot of that is done for monitoring river water levels, flooding, sometimes farm dams. So, and the team produces this output for continental scale for however long the satellite imagery has been available for. So something like 30 years of Landsat and last 4 or 5 years of Sentinel-2. So the Landsat is the NASA satellite and Sentinel-2 is the European Space Agency satellite.
Mm-hmm.
The other products are things like fuel things are being developed. It's not production ready
fire
yet.
Prevention and those sorts of things.
Yeah.
Oh, right.
And then burn scars, again, stuff being developed. Anything that has happened and you can't possibly have people everywhere at once, you can sort of post facto observe it and sort of work out what happened. Yeah, it's like this camera, this stream thing. So yeah, that's sort of capturing reality and then getting more understanding, intelligence about it.
Yeah,
after the event.
Yeah, developing insights from whatever the data is that you're getting. Yeah.
Yeah, and also some sort of, let's say, priority planning, because thanks to all the satellites and stuff, we have good observability of what is happening compared to never before. So there is like, a flood in Sudan, and it's being said is never before. And we are like questioning, is it really never before? And you can try to answer that, but also you cannot answer that because there might have been clouds. The satellites have not always been there for the last 100 years. And some of the data collection stuff is, again, it's all about like this data collection thing, which is sort of like the energy monitoring thing as well. It's like data collection and observability and making smarter decisions based on that thing you have hoarded, but you have to be able to analyze it as well. Yeah.
Okay. Well, that is a really interesting point. And I think a lot of the time that when people get into home automation projects, they do it just because they can, or it's fun, or it's interesting. Like that's largely my motivation. But when you start recording data, we'll talk about the specifics of the hardware in your project in a little bit, but I think this is interesting. So when you have historical data, you can see trends and things over time. Then you can start to make decisions based on that information. And it sounds like that's the sort of thing that a lot of your day job involves. And I'm curious to know how that ties into your energy monitoring as well.
Yeah, so the energy monitoring sort of started as an interesting side project in sort of looking at what my house was doing. We were living in Adelaide back then, and my wife is a statistician, so she wanted to have a look at some data.
She wants all the data.
Yeah. So she was like going around turning stuff off in the house at the plug, and I'm like, oh, my media center is turned off. You can't do things.
Yeah.
So I was like, oh, I will get an energy monitor and see if that's really the problem, or is it the fridge, or is it the Bitcoin mining I'm doing?
Yes.
There was a
Bitcoin.
Yeah, not recommended anymore. Anyway, no. Unless you own like your own hydropower station somewhere. Anyway, so that's sort of where it started, and I looked around at what was available in the market. There was FRG, there was Open Energy Monitor. And I was like, I have this almost PhD in electronics engineering. I surely can do better.
Yes. Yeah, you're a real EE. I only pretend to be one on YouTube.
Yeah, I did my electrical and electronics in Adelaide University. Yeah. I had a friend who did English and E and EE, so it's like a 4E.
4E.
But anyway, I am a triple E. Yes. So so I was like, surely I can do this. I have not done PCB design and stuff since I finished engineering school. So I sort of got back into it, and I built something around the single ADC you get in a ESP8266.
Yes.
Which is not a very good ADC.
It's very limited.
Yeah. And then I sort of progressed into using an I2C ADC, the ADS115, which is a pretty slow ADC, but it sort of was good enough. My son was born around then, and I was not getting much sleep at night, so I was like, I'll draw lines in Eagle. That was Eagle back then. Yeah. So collecting data to satisfy a curiosity. I looked around in the market. I could have just gotten an FRG or something off the shelf. At some point, actually, along the line, the people from Open Energy Monitoring Project based out of Wales picked up on my work and bought some of my stuff, and then sent me their hardware to have a look at. It sort of is a higher bar, the Open Energy Monitor, because it requires like an Raspberry Pi to run on. Whereas mine was just running on top of a USB, and it had Wi-Fi sort of as for free because you were running on a USB. Whereas the Raspberry Pi solution didn't have Wi-Fi. So this was in 2015. The Raspberry Pi didn't have built-in Wi-Fi till a bit later, and so on. Yeah.
Yes. Yeah, that's right. It came in with a later model. Yeah, so then I'm curious, since you were looking around at the time at things like Open Energy Monitor, what was the reason for starting your own project rather than picking up one of the existing ones? Were there things that they didn't do that you wanted to achieve?
Well, that I will bring in that I was not an expert, so I hadn't done anything in energy monitoring, so I trusted my own skills more. I was like, I can do better.
That seems to be how I start most of my projects. I know nothing about this, so surely it can't be that hard.
Yeah, so it was a bit of that, and then slowly it sort of turned out that the Arduino ADCs are not so great. Rani, do you have a minute? Oh no, we're getting ready. She helped me a lot with the stuff. She did all of the hard work, soldering and crimping. Yeah.
Oh, great.
Anyway, so the Open Energy Monitor is great. They have been around it for what, 10 years now or more? Yeah. The limitation of the Open Energy Monitor is that, for example, they rely on Arduino's ADC,
yes,
which though really easy to use, has the shortcoming that it's actually a single ADC on the standard ATM9328 Arduino, and it's like multiplexed.
Yes,
so it just swipes across the pins. So you can't do concurrent sampling of the current and the voltage. So there will be a little bit of delay. So you have to fudge around with delays in software. And you would have to write software to actually compute energy. So my newer versions of stuff actually uses let me see.
Yeah, let's see some hardware.
Uses this ATM90 chip, which is a dedicated ASIC for energy monitoring. So it does all of the computation on board this ASIC. How far can I get? Anyway, there are better pictures online in this video. So it is an ATM90E26, is a sort of a energy monitoring ASIC. So I was looking around at ASICs after I encountered this problem with the slow sampling in the single ESP ADC, which can go a bit faster, but you need 2 channels. And then at the ADS115, the I2C ADC also was quite slow. So after I encountered this challenge, I was looking at additional stuff. So I could have gone with the Arduino and made it a slave to the ESP and sampled on the Arduino's ADC. But I sort of came across the other stuff. There are analog devices as a series, like pretty much every electronics manufacturer, ASIC manufacturer, has some sort of a play in the energy monitoring ASIC field. Yeah, so the ATM one was pretty good because back then Atmel sent me lots of free samples. It was like, oh, well, nice. The bar for getting one was really low. And they're really cheap compared to Arduinos. They're like $1.50 or something, the energy monitoring ASIC. So for Arduino is good for general purpose stuff, but if you are just doing energy monitoring and you don't want to write code to do the energy monitoring and you want to do it real time, the other reason I built my own hardware was Atmel, even though they sent me free chips, their dev kits cost like $800.
Wow.
Yeah, because the people buying their dev kits are like meter manufacturers, right?
Yeah. To them, $800 is nothing.
Nah, it's
just part of their R&D budget.
Yeah, so I will get 1 dev kit or 5 dev kits, and I'll give them to the in-house hardware developers, and we will sell each of these meters for $400. So, oh well, it's a real, what would I say, billing meter. Most of the complexity is not in the energy measurement itself; it's in tamper-proofing.
Oh, okay.
Yeah, so all of the casing and shielding and doing this sort of lockouts and all those things. So a digital energy meter is the one that they use for billing to meet compliance. It's accuracy and all of those things, but also a lot of the bulk of the thing is actually in tamper-proofing.
Yeah, you have to be able to trust the data.
Yeah,
and so I guess that what you're saying is that you can achieve the same sorts of levels of accuracy if you don't care about the tamper-proofing. So if you're building your own device, you can use these chips. You can be just as accurate as one of the expensive commercial meters. It just won't have the tamper-proofing.
Yeah. The other element that they have is like very good sensors. So the electronics is a part of it, and then this is a mixed mixed signal
Mixed
design. So
signal.
there's
Yes.
it's analog and digital. So the analog parts have to be fairly accurate as well. So you have to get current sense resistors that have good thermal stability.
Yes.
You have to get good clamps, which like fit the size of your wire so that there is no leakage when you're doing that sort of stuff. Or the commercial ones probably will use shunts as opposed to clamps because the shunts are more accurate. But then they add additional bulk to the thing. The clamps are getting quite good now, but yeah. So then that sort of stuff is also, so you have to have good digital stuff, which is on this ASIC, but you'll also need to have good analog stuff and good less loss in the signal path, or good calibration, a lab to make sure anything that you haven't accounted for with good sensors is calibrated at a per meter level.
Yes.
So you'll have to spend time calibrating each and every meter to make sure that all of the analog vagaries or discrepancies, that the 1%, the 0.1% in resistors and stuff is taken care of.
Yeah. So we have a question from James who said that you're talking a lot about sample speed. So what sample rates are we talking about? Like, how frequently are you sampling this?
So that's a good question. So there's like a big sliding scale of how far you can go. So like the ESP ADC, for example, I think the fastest you can run it is around 1 kilohertz. The ADS 1115 that I looked at after that, you could do around 330 hertz. So just in keeping in mind that we are looking for 50 to 60 hertz actual base, right, signal to process. So if you're running at 330 hertz, then in a full cycle of the AC, you would get like 3 or 4 samples if you're lucky. So the ADS 115 was like barely working. And then this one's use like a 8 megahertz main crystal. The main crystal is 8 megahertz, and then it uses it in the ASIC, and it ends up sampling at around 8 kilohertz. And the three-phase,
that's much faster.
Yeah. The what is it called? The ATM36, which is a 3-phase version of this, samples at 16 kilohertz.
Okay.
And that's considered good enough for, like, billing level metering. There is a tear down I did of a Sense energy monitor, which is manufactured in the US. It's like the best hardware you can get for energy monitoring sort of deal. And they have done it at a pretty good, reasonable $200 mark or so. You can't get them in Australia because they're not designed for Australia. They're designed for split phase US AC, right? So the funny US,
the 220 volt strange thing.
110, the strange thing. Yeah, so they're designed for that. So they use a dedicated ADC with a high speed. So they sample at around 2 to 4 mega samples per second. Yeah, so they use a dedicated TI ADC and then pipe that into a CPLD. So it's like a sliding scale. Like you can go crazy on how fast you sample.
Yeah. So what we're talking about here, just to clarify, partly for myself and partly for everybody else, is that when I think about sampling for energy monitoring, there are really 2 totally different sampling rates. One is the sense side, which is what you're talking about here, where you're measuring the voltage and the current. So you're basically measuring the waveform. And that needs to be done very, very quickly to build an accurate picture of the power that's being used. And the other sample rate, which is, I think, what most people think of, is how often am I getting a reading out of it? Like, am I getting a reading every 30 seconds or every second or every 5 minutes? And those 2 things are very, very different. So I think it's just important to mention that so that there isn't confusion about sample rates. We're talking about sampling thousands of times a second, and some people are thinking, why would I want to have a reading thousands of times per second? It's a different part of the problem.
So the what did I say? Errors accumulate. So if you don't sample fast enough, you are missing the picture, and it gets blurrier and blurrier. As you move up the stack, and your ability to hold all of the data bits weaker and weaker. So if you have a good one close to the analog and move it to the digital domain at a higher speed, then your ability to bring it to the cloud or to your own storage in-house, like sort of, is better and better. And then you have to make your pipes better and better to store as much as you can, where the data is still valuable without being too much. Yeah, so like some of the so I advise this after I put this stuff out. So people everywhere contacted me. So I was advising this group or person in India from Chennai. He started a company called Minion Labs. He wanted to emulate the Sense thing. So he built something using an FPGA and stuff, and then he was saying, oh, now I can only get the data to the cloud at like 400 times per second. That's the fastest their solution got to. So you are getting 400 power readings or energy readings, or not energy, but power readings per second. So it's sampling much faster because they have like this sort of analog plus like a FPGA solution, and then it goes into this Octavo Systems package on package thing that they built on top of the TI stuff, and then that's runs Linux on that, and then the fastest they can get it out to Amazon IoT is 400 times per second.
Yeah.
So that's like the fastest they could get, and they were like, "Oh, what do we do now?" Like, so there again depends on how fast. You can't get the 4 mega samples per second out, and even the 400 times per second. What are you trying to achieve with that? So
my question there is, what would be the benefit? Because if you've got a large number of samples, ideally you would want to process those samples as locally as possible. So you're not outputting all of the raw data, you're outputting the outcome of the raw data.
Yeah. So some of it is like what Sense does. I'm sort of drifting away from my own project to like the state of the art in the industry is what is called NILM, non-invasive load monitoring. So it's like a machine learning based approach to see all the different devices you have without essentially monitoring each device separately.
Yes, this is a really interesting topic. And so just for background for other people, I've mentioned on previous live streams, devices that you can install that will monitor the power consumption in your house and can detect the signature essentially of different types of devices. So it'll say you have a Whirlpool washing machine and you have this particular electric stove, because it knows the power profile of those devices and it can tell when they are being used. So that is really quite spooky technology.
So then you can't probably tell that with the 400 samples per second, I think. Which is why Sense went with their 1,000 megasamples thing. So then what ends up happening in that sense is, in that particular instance, is you build models or of whatever sort, TensorFlow Lite or just like random forest classifiers, whatever sort of thing, using the high frequency thing locally in a lab. I don't know how you'd afford all of the plants out there in the universe, but anyway.
I can just imagine, go down to the local white goods store and say, I'll have one of everything.
or like just go to the white goods store, go to the good guys and say, would you like to install my meter?
Yes.
And then anyway, you train something and then you move that model into your local processor, such that the local processor is actually not saying energy reading here total, or saying Whirlpool washing machine this much, this much, and then sort of running the model, running the pre-trained model locally and just giving answers back.
Yes. Yeah. There's a lot less processing required to run the model than to create the model in the first place.
Yeah.
Okay. So I'm really curious to know a little bit more about your project. And one of the things that interests me is the form factor. And so you've built a device that's DIN rail mounted, which makes it easy to install in Australian switchboards, at least, because we standardized on DIN rails, not so much in other parts of the world. But could you maybe just describe your device and how it works? And how you...
Sure. Let me see. I have got, okay. I've got boxes here. I haven't, just a minute. Doodling around. Actually,
sure.
good thing to maybe show what DIN rail actually looks like.
Yeah, and while Tish is grabbing some things out, if there are people who have got questions, please drop them in the chat and I will pass them on.
So DIN rail looks something like this. So the word DIN is something in German. I tried to memorize what it stands for, but
I think the D is Deutsch. That's about it. All I remember.
So something about Deutsch. So it's popular in Europe too. So there has these clips on top, and all of your fuses and stuff are there. But DIN rail space is a bit of a premium in a household.
I'm just going to grab something.
Yeah.
So this is a piece of DIN rail. And this is what gets mounted in the switchboard. I'll hold this up for people to see. And it's got this profile that a plastic container can clip onto. So this is fixed permanently. And then what Tish is showing over there clips onto this. And it means that you can have this mounted on a wall and then clip boxes onto it.
Yeah. So this one is a few units of DIN rail. So this one will be 3 or 4 units of DIN rail. A single unit would look something like this, would be a single unit.
Yeah, like a standard circuit breaker sort of size.
Yeah. And then, so that's sort of the DIN rail. And you can get DIN rail mounted energy monitors from AliExpress. They don't have Wi-Fi. They are not your own hardware and stuff. A good company for that is Eastern. So when I started building mine, I got a few $60, $20 ones from Eastern to take them apart and see what that was made of. There's also a very good Australian company called Watt Watchers. That do Australian designed DIN rail mounted ones. So the base of the thing is this thing. So you can see sort of the DIN rail size. I'm just gonna, this is fresh from the PCB house, so I'm just breaking it up.
That was 2 units.
So that's sort of the base of it, and this supplies power. It has got the AC stuff. AC stuff on this side, the green side, and the current clamps plug into this nanofit connectors. That's sort of another obsession of mine, connectors. Good connectors, you have to go through and find the ones that are good and provide a solid thing and have lots and lots of cycles you can put them through. So that's sort of the base of it. So some of the ones that you will find Eastron makes or others make use a transformer. So this is a switch mode power supply.
Yes, so I've used the same power supply myself in the past.
Yes, very high link. It's a bit noisy, but it does the job. So again, so those are the analog things to keep in mind, that there will be noise from your switch mode supply and all of those things. So you have to make sure you put in some filtering so that whatever you're sampling is what you're getting. So the net thing is that you are essentially grabbing the voltage and creating 5 volt, 3.3 volt supply for your energy monitoring on this. This is also quite interesting. There is another small supply. I don't know if you can see it. You can see it in the PCB designs. It's a small one. This is a DC-DC isolator.
Okay.
So that you can sort of play around over USB while it's connected to the LV, the 240 volts. You have an isolator which sort of powers the LV stuff, whereas the SMPS actually powers the ESP or ESP32 that you are using as your controller. So you can actually have it connected and stuff is isolated. So you have to put in some slots and stuff in underneath to create a bit of isolation. There's an SPI isolator in the design as well, so that your SPI bus that you're talking to.
That's very interesting. So
Yeah,
it's
yeah,
handy to know about devices like that. They can be very useful sometimes. Yeah.
yeah,
So
yeah,
just to help me understand a little bit more about how this is installed,
yeah.
on that particular device, you've got the high-link switch mode power supply. And
Yes.
then how many channels will this device do? Is this a 2-channel device?
So the base I designed to be shared between double 3-phase and any other double single phase. So it's modular design. So this can power an energy monitoring ASIC. So there is no energy monitoring ASIC here. It's designed to sample the voltage and the current and to pass those analog signals up to a digital stage. And also provide an isolated separate power supply. And in this particular design, I have like a sort of a battery backup little section here, which is sort of to, if you have LoRa or some other non-Wi-Fi thing, is for point of load outage notifications if you wanted to do that sort of stuff. Because currently the utility doesn't know when a particular household doesn't have power. Yeah. So yeah, so that's sort of the base. So you can then, so this connector here is a PCI X1 connector. They're sort of quite cheap and easy to get and provide good solid standing offset. So then you can sending all of the dense signals up through this PCI X1 connector.
Okay. Yep. Interesting. Yep.
Yeah, so that's another tip I picked up from sort of disassembling the other energy monitors. They use similar riser connectors. Yeah, so then you sort of move on to the actual energy monitoring ASICs, which I'm still twiddling around for.
Okay. Well, while you're checking for that, Aaron asked about this being based on 240-volt AC, and will it be UK compliant? So how do you handle situations of using this in other electrical systems?
The SMPS is rated from 90 to 240.
Yep.
So people have successfully used it in the US and I guess elsewhere.
So it's really only software that is the difference between, great. So the exact same hardware will work on UK or Australian or US or whatever electrical systems.
Yeah. As long as there's not like 50 volts. So just interesting things I've come across. There is a Sydney and Cambodia-based company called Okra. They're doing 50-volt local grids in parts of Asia. So yeah,
that's odd. By local grid, do you mean like just within the house or?
No, village level grids.
Village level.
Village level microgrids. So you know, your PoE, power over Ethernet, operates on your 50-volt being providing less loss and letting you let the power through hundreds of meters. So if you have houses separated by hundreds of meters, you can build a local grid using 50-volt.
Interesting. I hadn't heard of that.
So this is the energy monitor ASIC, right, which fits onto here.
Okay.
Like that, like so.
Yeah.
Yeah. So so that's like the riser, and it provides a bit of stability. There's a bit of wiggle, but it's not much. So the deep riser provides mechanical strength, and then you can just like plug and play these. So the aim of making this was letting me able to experiment with other energy monitor ASICs or even FPGA, CPLD, crazy stuff. If I managed to make one or someone else wanted to make one, they didn't have to build this base stuff from scratch. They could reuse it and go, I am just going to sample at 4 mega samples. That's what I'm going to do. So you just build this part of it, the going from the analog to the digital part. You rebuild that with high-speed ADCs and an FPGA or a CPLD, and then you proceed from there. So that was sort of the idea.
Okay. Yeah, I like that idea. It gives you lots of flexibility.
Yeah. So and then it goes on to sort of like a front end. So you sort of move into this sort of stuff. This board here I designed, which is essentially an SPI isolator. So it uses ST microsystems stuff, which and it has a little slot here. I don't know if you can see that.
Oh yes, I can see the slot.
Yeah, so it's a SPI bus isolator. So it essentially does. You flip it on here. So after you have gone from analog to digital, something that you want to use in the digital domain, you basically go, okay, now I am gonna this bit here. It was a lucky mistake. I put my connector in the wrong way.
And it just worked out nicely.
It worked out nicely because then it was not too deep for the DIN rail enclosures I was using.
Yeah.
It's very hard to design for the DIN rail a particular enclosure where you start from the enclosure and work backwards to make electronics for it.
Yes,
because
the shape of those enclosures is very strange because they're designed to protrude through the slots in the switchboard. So yeah, I've designed a couple of DIN rail mounted devices, and you really have to think in 3D. You can't just design a flat PCB.
No. So I had to go through a bit of process iterating, like even like shrinking this board down a bit to fit, and then doing weird things with soldering the header. So I was trying to use as much as off-the-shelf things I could for the processor boards, which I find most difficult to make myself, because things that go in sort of megahertz and stuff with delays and all that sort of stuff, you have to. I haven't designed too many of them myself, right? So so I find that those things more difficult to do. I am not a dedicated electronics engineer like in my day job, so I don't do those things all the time. So I wanted to use things that were off the shelf as much as possible for those bits, and then do the analog digital lower speed stuff, and then get to that, and then have some sort of a module or SOM to handle that. So the initial SOM I used was obviously the ESP WEMOS.
Yes.
So let me see if I can have some of them floating around somewhere.
So I think this is going to tie into another question from Aaron, who said, is it Wi-Fi only, or are there ambitions for CAN or Ethernet versions? And I think you're partly going to answer that question now. ESP.
Yeah, so let me just show this one while I'm here. So this is still also on its PCB thing. This is a double three-phase one. So it uses the ATM90E36, so which is what I was sort of alluding to, saying it's a shared base, and then you can design or choose your own adventure regarding what sort of sampling and ASIC monitoring you want to do. If you wanted to stay, say, within the open energy monitor ecosystem, this could be an Arduino, right? And you just use the ADCs in the Arduino and sample stuff, and then talk to ISP for Wi-Fi over the UART or something. So so that's sort of, you can choose that. So so that's the double three-phase. So the baseboard provides enough voltage and current samples and channels to also do double three-phase.
Okay.
So the ESP, I guess I don't need to. I'm still digging around here, but the ESP don't need to show. It's just the standard WEMOS. These are the things that come from in the box for the OLEDs that go in front. So there's the OLEDs. So that goes to the very top, and you get your little OLED display. So that's sort of the put together. So in order to make the OLED really flush, I was doing you have to do weird soldering where you put in the headers again backwards, so that there's a very small gap between the WEMOS and the OLED. They're squashed together, and then that way you get lower the vertical profile of your overall stack up to fit within the DIN rail. Lots of hacks.
No, it's not hacks. It's engineering your way around limitations.
Yeah. Oh, Ethernet and other stuff. Okay, so I started doing sort of there were a lot of interest in having like a Linux host instead of the ESP host, right? So as I was saying, the Open Energy Monitor project uses a Raspberry Pi host. So that sort of a Linux host, which is what I was giving my talk on in LinuxConf about, is a bit is interesting. And then you can add CAN bus and all of those things, or you can add Ethernet if that sort of Linux host. So the typical things in the market for that purpose are Highlink has a new module. I don't know if anyone has seen them. This one. It's like a MediaTek SOM. So you can, it sort of fits in size. So it should fit.
You can make it work.
You can make it work. So that's sort of the MediaTek SOM can be used with its Ethernet and other buses that it has. It has got some trouble with the SPI bus because it also shares the SPI bus for its boot flash. So if you have the SPI bus loaded while it's booting, it will not boot.
Okay. You have to keep all your peripherals isolated.
Yeah, you have to have your peripherals isolated using tri-state isolators or something similar. Let it boot, and then use a GPIO to put the peripheral on afterwards and stuff. So that's sort of that could be something that you can use. So even it's modular, and you can swap the front end or the CPU that you're running it. So I've actually successfully swapped between the ESP8266 and the ESP32 because both are available in the WaveMOSI form factor. I haven't successfully swapped to anything else yet because I'm still, it's a hobby project and I am still messing around with you could that's why it's good to have a talk like this if you want to. There are things
other people have their own ideas about what sorts of things they want to do, so they might have.
So you can happily get up to this stage and then go, oh yeah, I feel confident designing around different SOM. I will wire up the SPI bus to that and then move ahead.
Yeah, cool. Okay, well that leads into another question. James O'Gorman said, what is double three-phase? And Frank answered that he thinks it means you can monitor 2 by 3-phase circuits. Is that correct?
Yes. So like I was showing you this thing, this is the ATM90E36, which is a 3-phase monitoring ASIC. And on this riser, there are 2 of them. So the typical use case would be if you had 3-phase solar. And 3-phase supply in your house. So you're generating 3-phase and consuming 3-phase. And so you'd end up with 6 clamps or 8 clamps if you want to like double clamp the neutral. And then you can basically monitor your generation and consumption for 3-phase. So this also works.
I've been meaning to do it. I was wondering why there would be that 3-phase in a domestic sort of situation. But when you're doing your own local power generation, that is definitely a use case that could really benefit from this.
Yeah, if you put in a very big solar, you can only put in 10 or some sort of upper limit. I'm not a solar installer person. Some of this work was sort of supported by an Australian company, an Adelaide company called Suntrix. They sort of supported my work to do this because they do solar installations and they wanted to install this with their stuff. There is an upper limit on how much solar you can put on a single phase to not destabilize the grid. So if your solar install is bigger than that, you have to have a 3-phase solar installed with balance across the phases so that you are not, solar is all great, but it's it breaks the grid model of energy supply, and they try to like sort of manage that a bit.
Yeah. Okay. So since you've got the 2 ASICs on there, which can do 3 phases each, does that mean you can also just do 6 individual phases? Like 6 channels, essentially. If you had 6 power circuits in your house, you could measure 6 circuits.
So you basically tie your phases together. The ASIC gets a bit unhappy because it also monitors the phase angles. So it says, this constantly has warning bits set saying your phase angles are crazy. But otherwise it will give you the measurements just fine. It's not that smart.
Yeah.
Yeah.
What I'm thinking about is a use case like my house. Okay. So we've really got three use cases in my mind at the moment. So one is the solar local generation that you're talking about. Another is the most common domestic situation where you've got a single phase coming into the house, and then you have multiple power circuits and maybe a couple of lighting circuits. So in that situation, you could use your device to measure those internal power circuits, up to 6 of them, and then report on those circuits. And then the next step beyond that is the way my house is wired up, where I have every single end load wired back to the switchboard. So in my switchboard, I've got rows and rows of relays that control the outputs. So ideally, I would like to be able to monitor power across maybe 30 circuits. So in that sort of situation, I could start with something like your device to monitor 6 of them. And then could you maybe explain how you would expand beyond those 6 channels?
Okay. You would need more of them, so that's
More
sort
devices.
of limited to say. Yeah, more devices. I do have this one, which is like a work in progress. It's still on breadboard. It's a different energy monitor ASIC from Analog Devices, an ADE 7816. So the 16 stands for 1 phase and 6 current channels. So the 6 current channels. So if you didn't want to use the 3-phase one and make it unhappy because the phase relationships are all broken, you could use something like this. And then you can change the baseboard to pack the stuff together, so you can end up with like 12 in one device if you wanted to do that. So the ASIC is fairly small. Let's see. Yeah, it's a QFN.
Yeah, I can barely see it on the PCB.
I actually got the footprint of this wrong the first time I designed it, and I sent the board to Greg in Adelaide, and he did a dead bug of the QFN.
Oh, I saw a photo that Greg posted of the dead bugging. That was maybe a couple of weeks ago. Is that the right one?
That's the one. Yeah. I've caught up with. When you get to this level of stratospheric thing, a few people of us, and we know each other. Greg actually contracts for a company I used to work for in Adelaide, Aerometrics, making cameras as well.
Cool. It's good to have contacts who can do crazy things like that.
So that's okay. To answer the single phase, lots of dense single channel things. Something like the ADE 7816, and then there's a little bit of a gap here in my nanofits, and you can go and just pack more of them, maybe, or a different connector, and then just go, okay, I'm gonna put 2 of those 7816, and we'll have 12 channels in one, and something like along those lines. But it will require redesigning this base one, which I have done a couple of times. So one of the redesigns of this base one I did for EV car charging was essentially measuring and then turning relays off, like you were saying. So instead of it being double 3-phase, you would dedicate one side to your measurements and one side to the relays. So I just had like optocouplers driving bunch of off-board relays. So this is actually an off-board relay. So this thing is an off-board SSR relay. So and also this thing is a contactor, is a 4-channel contactor. So drive an off-board relay to do those things. Anyway, it's possible. Again, it takes engineering time to try those options out, and that's sort of the other challenge in working in hardware. Your engineering times and your cycles are slower, your iterations are slower and expensive. You can't just push new code and go, oh yeah, the CI went unhappy, oh well, that's fine. There's no continuous integration anywhere for hardware.
No, that's right. Like, one way I describe it to software people is imagine if every time you type make, it takes 2 weeks. So
yep. More sometimes,
yeah, more.
depending on the global logistics.
Yeah.
Something else I've come to appreciate doing these things. Yeah.
Yes, yeah, definitely. Certainly at the moment. Now, John Clark asked a question. Apart from the RF interference issues, how about a power line data interface? So have you looked at power line at all?
Not really. I sort of, what would I say? I have read about it. I have seen people do it. So I used to be, the lab I was in Adelaide was the signal processing lab. So they would do fun stuff like that. But I haven't looked at it myself. You could send the data out via the power line, and I have the Ethernet over power things lying around.
Yep.
Maybe I have seen those being used. So I have seen once one of my friends took me out to the Riverlands in Adelaide, and there was like a solar farm shared with a vineyard. Half of it was a vineyard and half of it was like a solar farm. So, and they had these container-based batteries. And because containers are big steel boxes, Wi-Fi was pretty unhappy in there. So the way they had the energy monitoring set up was they would go from the user Ethernet. They had a Raspberry Pi Open Energy Monitor thing, and instead of using the Wi-Fi on it, they would just use the Ethernet, power over Ethernet, and then out, and then to some antenna somewhere else.
Yeah,
outside the container, because Wi-Fi was unhappy, right? So yeah. So
well,
yeah.
Something I'd be very curious to know is a problem that has bugged me for years is how to get communication between devices inside a switchboard. In the classic Clips or C-bus sort of environment, C-bus is the solution for those devices. So you have a bus that you can loop around between the different things that are plugged into your DIN rail, and a whole lot of the devices that are coming out now, things like the Sonoff 4-channel Pro obviously is Wi-Fi, the Shelly Pro is Wi-Fi, lots and lots of your devices are primarily Wi-Fi. That seems to be the solution a lot of people are going for. And it just seems to me that it would be nice if there was something that was more equivalent to C-bus as a way to just hardwire a bunch of devices together within a switchboard environment. And things like Ethernet are probably not the way to go. It's too complicated and it's just too heavyweight for that sort of situation. Something like a shared serial bus would be nice. And I was just wondering if you thought about that sort of problem at all.
Yeah. So one of the, what would I say? The standard around, say, inverters and stuff is Modbus.
Yes.
So they use the Ethernet connector, but it's not Ethernet, so they have to like clearly label Modbus, not Ethernet. But they use the Ethernet connector, and that's sort of what they do. One of the energy monitors I did with the double 3-phase, I did some contract design for a Brazilian company, and it's being deployed in Brazil by the utility there. It uses 3 of these plus another one, so it has 3 units of DIN rail for Modbus. So it talks to the generation part, the inverters essentially over Modbus, and then exposes it over Wi-Fi.
Okay. Yeah. So it uses Modbus locally to
concentrate the data, communicate across multiple inverters, and then because the inverters monitor a lot of stuff. So generation, the inverter knows more about it than you will find by clamping the wire.
Yes. Yeah, definitely. Yeah. Okay. Yeah, so it's nicer to talk to it than to try measuring it in that situation. It can just give you the answers. So Aaron wanted to know about other form factors like wall sockets. Obviously, what you're focusing on here is monitoring whole house power usage rather than like endpoint load power usage. So the circuit that you've designed could presumably simply be installed at the endpoint, but the form factor is quite different. You've got a DIN rail form factor instead of a PowerPoint type form factor. Have you thought about doing end load monitoring?
Not really, because there are a lot of solutions already in the market for that. They're very cheap.
Yeah.
I've done lots of tear downs of them. I get given them again. Suntrix is really good. He buys stuff. So David there buys stuff from China or whatever and gives them to me. Say, oh, look at this. Thanks for helping me. And so I write tear down articles for them. I've looked at the TP-Link one and the Kogan one. They're fairly simple. Like the Kogan one, I think you can load your own firmware. So
yes, you can. Got them, and I've done it, but they are very, very inaccurate. I was actually going to talk about
I don't know that.
Sometime
Yeah. Yeah. So like they use not microchips. Like they use a different energy monitoring ASIC, but they do use an energy monitoring ASIC. And then there might be problems with their sensing accuracy, the analog stuff that they have in there for their thing. And the Kogan one, that energy monitoring ASIC actually has been discontinued.
Oh,
so,
okay.
Sometimes some of these manufacturers, I find Maxim especially, or some others, make a foray into a new field, release it, and it doesn't gain traction, and then they discontinue it. It's really, as a hardware designer, engineer, it's really disheartening. You invest so much time in mastering this particular thing they have done, and it doesn't meet their business case, and it just disappears, poof, and it's you're never gonna get back that time. Anyway, it's a hard feel.
Yeah,
that's tough.
Yeah, with the Kogan energy monitoring devices, I found that they massively over-report the voltage. Like I can, if I've got one plugged into mains, it'll be reporting somewhere in the 290, 294 volt region. When I stick a multimeter into the same power point and it tells me it's like 238 or 244. So
so maybe their analogs and their calibration is off, or they haven't calibrated each unit.
Yes, that's true.
Yeah, so if they're using say 10% resistors in their voltage ladder somewhere, and it's off, and then they have multiple of those, maybe, I don't know, I have to double check my tear down, then all of those errors will add up. And then if you have 10% resistors and 4 of them, you'll get 40% error.
Cool. So James asked a question which actually comes back to what I was going to ask earlier. He said it's a question for both of us. Do you order prototype boards with parts already mounted? So those panels that you were just showing a moment ago, do you do any of your own assembly, or do you order those from an assembler?
These ones are made by PCBWay, fully assembled. The first iterations I did by hand. These ones use 0402 parts, and they're quite hard to do by hand and get good yields. I am not Greg. And what would I say? Since moving and having a rental property, this just real estate, you need to do that, has been a struggle. So I have been more lately doing more of it. I wish Rani was here. She was my partner in hand assembling when I did my crowdfunding. She's a teacher, so she did like statistics, maths, computer science teaching. Now she's a primary school teacher. She did this amazing like color-coded write-up on the schematic to mark different parts with different colors to quickly pick and place, and so
really optimize the process.
So I do that myself. So I have fairly decent SMD skills to do it by hand. I have also sort of developed this dry iron workflow, which I use with the limited bench space I have. So essentially you take a non-steam iron and then you flip it around, and then you put your PCBs on that and use that as a hot plate.
Oh, interesting. Yeah, so that's like the skillet technique that was in a SparkFun tutorial something like 10 or 12 years ago. So you use a hot plate and put the PCB on it for reflow. Okay.
It's the minimum thing that takes up minimum disk space that I could get.
That's really clever. One thing that I've often thought I would like is a tiny reflow oven. Like the size of a toaster, like not a toaster oven, I mean like a toaster. So like
for making toasties,
So I could have a really tiny reflow oven that I just put a single PCB into, I've got the big reflow oven, but that's like 3,000 watts, and it's big. It's 1 meter wide. So
yeah,
it would be really handy to be able to do reflow. I might have to think about finding some old unused iron and use that.
Yeah, it's about the same cost as getting a soldering iron. They're $10. So I bought mine. I was running. Why did I get it? Yes, I was running a open hardware meetup in Nairobi.
Yep.
And I wanted to teach SMD soldering.
Mm-hmm.
And we did paste and placement and everything. And then we were like, how are you going to reflow this? So doing hot air reflow with new people doing SMD is hard because they may just blow the parts off.
Yes.
So the first time we did it, we went to a secondhand thing, bought ourselves a skillet, went into a restaurant downstairs from where we were doing our thing, and said, can we borrow your gas stove, and put the skillet on it. And we put a secondhand thing. And then the next time we ran it was in a pub, so you couldn't just randomly do stuff. So we brought our dry iron and did it on the dry iron. It works. It doesn't really have any insulation. So you have to have good ambient temperature, high ambient temperature for it to work. So you may need to turn on your aircon and stuff if it's in winter, in Canberra winter especially, because the heat is being lost. It's an open
it just radiates
thing.
Away.
So you need to have good ambient temperature for it to work successfully.
Yeah.
Anyway, long answer. Yes, I do SMD. So.
Oh, cool. Yeah. So to answer James's question from my point of view, I think it's probably very similar to Tish in that I do hand assembly of prototype level production, and then for anything quantity, I get it done elsewhere, so contract assemblers. Sorry, I'm just having a quick look at questions because there are a couple more I need to catch up on. Aaron asked, accuracy was the reason I asked. I assume Tisham's solution is more accurate. I think this is tying back to the Kogan comments earlier of me saying that the Kogan monitor was inaccurate. And do you have any particular objectives or standards that you're trying to hit in terms of accuracy? Like, is there a benchmark that you're aiming for, or is there something that you really just did because it was an interesting puzzle and you wanted to solve it?
No, I'm not. Others using it are people like Centrix who would like to do it. So these are all like value adds. Accuracy and these things are all value adds, and depends on the market you're trying to satisfy. My market was it was more an E2E thing. That I was addressing other engineers trying to build this stuff, and they can value add by adding accuracy, self-calibration, what have you, or calibrate for their house when it's installed. So as I said, some of the value that comes in when you buy utility pay money for the number meter is the calibration. And so that sort of calibration needs to be done per meter ideally, because for the parts, the analog parts, even if you pick the 1% or the 0.1%, it's going to add up over the month that you get billed over. It's going to add up to tens of dollars, and no one wants to be overcharged or undercharged. So so you need to burn these things in and get the calibration properly sorted with temperature in consideration and so on.
Yeah, cool. Oh, I saw Pascal come around the back behind you a moment ago.
Yeah.
Hello.
Can you say hi?
He probably can't hear me because you've got the headphones in.
Yes.
Hi.
A hole in there.
What is that?
There's
have you got?
In that.
There's a hole in it.
It's a hole in the tube. Okay.
Fluffy.
Fluffy. This is what doing work is like at home. So this makes assembly hard, right?
But it makes it more fun.
Yeah, it makes more fun. What is the thing? It's disappeared between all this other stuff I have put on my desk. Anyway, so yeah, Pascal and I make fun toys like this one. Yeah. So Yeah, so this one is we went to LinuxConf, and in Gold Coast he found an abandoned quadcopter. So we took out its motors and then we mounted them here and made a car.
I see. So those are quadcopter motors. It must have been a very small quadcopter.
Yeah, one of those tiny ones that you get that have become modern day electronic junk, right? People play with it, the batteries run out, and then someone just leaves it somewhere. Yeah.
Oh, cool. Yeah, it's fun doing projects like that.
Yeah, upcycling stuff. Yeah. Any other? I think I have to head off soon. Are there any other questions around? Or I am available on Twitter, so you can just
not yet. Me. So I know, you have limited time today, so I should have warned everybody at the start of the live stream that that you can't actually hang around for the whole 2 hours. You have other commitments. So before
the commitment just came by.
So before we wrap up, what I'm going to do is, after all of this is over, I will update the video description and add links to Watnik and whatever else you like. Are there any particular things that you think people should go and look at, like references, your site?
Yeah, so I have a bunch of GitHub repositories. So what I'm looking out of this is like more people get involved in this space and actively build stuff. I'm happy to like provide advice. Like I said, I advise groups here and there. I'm happy to get pull requests into my Arduino code bases or MicroPython code bases. Happy to send people hardware, whatever I have lying around. If you want stuff like this, I have more than I can sell or more than people are interested in buying. But you can get this one. This one is still work in progress. If you want this one to play around with it at home, so it can talk to an ESP. I've written the driver in Arduino. Yeah, so what I'm looking for out of here is essentially more people getting involved in this, taking the leap, looking at what they can do, how they can contribute, documentation, experiments. So time, it's building that community of people doing stuff themselves.
Yeah. And at the moment, do you have a Discord server or a forum or anything else that community can get involved with?
Twitter is my thing. So currently, I don't run a company doing this or anything as such. I run a company which does a little bit of hardware just to cycle back into the next hardware iteration prototype. But I am happy to answer questions personally just on Twitter for everyone. People still send me emails, because that's one of the things of doing open hardware. People will send you direct emails and expect support.
Yes.
Please don't do that. Hit me up on Twitter.
Help everybody personally.
Yeah. So I'm happy to answer questions and let other people jump in. I've got interesting things, like I was mentioning Sense. I did the teardown, and their CTO contacted me saying, just be careful of that high voltage thing there, because that we don't have isolation.
Oh, well, at least you didn't get in touch and say stop doing it. It was just be careful of this. That's nice.
He's a cool guy.
Yeah. Okay. Do you have time for a couple more quick questions before you go?
Sure. Yeah. Maybe another 5 minutes. Yeah.
Sure. So Peter said, my cheap effigy monitor needs to set a voltage. Voltage varies all over the place. Does your monitor measure voltage and then does a calculation of energy based off that? My effigy is very inaccurate. So
so that's one of the things that why I didn't choose to use the effigy, right? So in my initial things, it's battery powered, it's nice, it's easy to install. You will require an electrician to install mine, because in Australia you cannot
that's right,
do that. So the effigy is easy to install. So some of these things is like this curve again of ease of installation versus accuracy and all of those things. The voltage varies according to the temperature of the day, the amount of loss in the power lines. You will see interesting things happening. If you look at the weather and look at the voltage, you can see, it's hot and the voltage will drop.
That's really interesting. Yeah, so the temperature of the wires goes up, which increases their resistance.
Yeah.
Okay. Yeah,
yeah.
it's, I think that's one of the most fascinating things about measuring a very wide variety of data sources, and you start to see correlations between them. And there may be causation, there may not, but
Yeah.
sometimes there is, and that can be fascinating.
Yeah. So like in a grid, that's why that you transmit at high voltages, right? So
yes.
So to reduce the wire loss. So in summer, but you don't have any choice from the last transformer to your house, and there's still some loss in those wires, and that sort of change. And FRG cannot measure the phase differences because you're not measuring the voltage, so it's going to only measure apparent power. So that will also overestimate, especially if you have a lot of fluorescent lighting based loads. So those things are notoriously low power factor, right? So they're energy efficient, but not easy to monitor because their power factor is low. Same for LED stuff, which uses switch mode power supplies built in.
Yes.
So they are also hard to monitor because the switch mode, what would I say, has spiky capture. So if you don't sample fast enough, you're not going to actually measure the real thing the LED is consuming. Right? Because the switch mode power supply is like hitting the bus in spikes and just grabbing power bits and pieces. So yeah, very choppy. Yeah, very choppy. That's a good word. Yeah. I'm just waving my hands to describe that.
And try to draw the waveform. So a couple of quick questions. Frank asked, do you have a website? And I think it's whatnick.com. Is that correct?
It's just my blog. Yeah, whatnick.com will go into my blogspot thing. I don't have too much resources to maintain things. GitHub is the other place. GitHub Whatnick would be, you'll see all of the stuff there. It's not very well curated. I'm not. I'm very bad at making an emphasis.
Both of those places into the video description once we're over today. So if anybody wants to go and check out Tish's work, the links will be there. Aaron asked whether you use MQTT to send telemetry at home, and if so, what are you using for logging? So we've talked about all of the data acquisition hardware. What happens to the data once you get it out? What are you doing with it?
Right. So I have mostly left it up to the users to write in their own firmware. So I think recently my friend Kelvin and Adam, who are both in Canberra, did some work around Tasmota to support Tasmota on this energy monitor and support MQTT out of that. The initial design that I did, that I crowdfunded, was just using plain HTTP to ThinkSpeak, which is like now dead or whatever. So you can do whatever you would choose to do. The guys I was talking about in India, they're doing MQTT 400 times per second to Amazon IoT.
Okay.
So it depends on what processor you have and how efficient your code main loop is. You can do MQTT, it's fine. I think they're doing that in like Python using like Paho and just like off the shelf things. Just their CPU clock speed is super high, so they can get around it.
Yeah, I think a lot of people underestimate what MQTT can do. They think of it as being something where you can send maybe a message a second or a couple of messages a second, but it scales way, way beyond that, and you can put all sorts of information over it. So that's a whole other subject we won't get into now.
No. It depends on what backend you have. The MQTT servers you have at the other end. The cloud providers are doing a good job there, and even the open source ones are quite good now. And the good thing with MQTT is it's bidirectional, so you can actually subscribe to your relays to be turned off and such. So it's quite cool that way.
Yeah. So I think maybe the final question before you have to rush off for family obligations is, how does your family like it when you're powering down the house all the time to install updates? This is a question from
you don't have to power down the house. So you can do OTA firmware updates if you're reasonably confident. And the updating the hardware, new ones, I don't install. It's actually in the family. My initial ones were installed by my brother-in-law, who is a certified electrician.
Yes.
So that sort of helped get the initial one in place and experiment with stuff. just normally. So yeah, in return, I got him some clients to install for, because he knew what he was doing and would like carry it on his what is it called, liability as an electrician. So that's yeah.
Okay,
Yeah.
interesting. Yeah, and I think that's
nepotism. No, I don't know.
but that's a really interesting point in terms of not the liability, but in terms of the electrician doing the installation. Once the base, because of your modular design, you could swap out the riser board without disturbing the base board, which has already been wired in. Yep. And I think that's a really nice feature from the point of view of a development platform.
Yep. Yep. So you can, I can keep on updating the firmware, which is isolated, and then you can keep on. Yeah, OTA is also good, quite good. And if once we get to a Linux host on the top board, then you can update stuff over SSH. Yeah, which will be good. A lot of Adam, especially, and others were like worried about breaking their stuff over the OTA if you make your mistakes in your custom firmware. So if you have SSH and a Linux stuff running on top, you have much more like upgradability or flexibility as a software engineer. Yeah.
Yes, that's right. Yeah, you can update within the environment instead of just blowing the whole environment away and replacing it, which is what typical OTA updates do. So it's what would I say? It's risky, and especially once it's installed in an unreachable place, it's you have to be careful with those things. Yeah, and opening up your switchboard and plugging in a USB cable is never a comfortable thing to be doing. You don't want to be doing that.
I have a favorite story about trying to update hardware and failing. There was a story back when, maybe 3-4 years ago, of people in Iraq receiving drone feeds from predators because the firmware was transmitting stuff in open, and they couldn't update the firmware on the predators, right? They're up there.
That's not a good day.
No,
that's happening.
It's installed and it's in flight. You update the firmware and it crashes, right? It literally crashes.
Yeah. A couple of years ago, at LinuxConf in New Zealand, Andrew Tridgell did he was flying a drone that was in Australia. So he was flying it by remote control from New Zealand, and then recompiled the firmware on the drone while it was in flight, and then switched to the new firmware live in flight. Yeah, that was a crazy.
It's a modern drone. These predators were probably built in the 70s, right?
That's true. That's true. Yeah. Predators are old tech. Yeah.
Cool.
Well, thank you very much, Tish. It's been really cool to talk to you again. Thanks for coming along. I appreciate it.
No worries.
I will definitely add links to your description. And perhaps, do you ever use Discord? Have you?
I used Discord for PyCon. I used it for KaiCon. I have too many chat clients and Slack, but I'm happy to join another Discord. Cool. Yeah.
So what I might do is I'll create an energy monitoring channel in the Superhouse Discord just for anybody that wants to talk about this sort of thing, because it is a really interesting topic that many people are into. And if you feel like dropping in sometime, that would be fantastic.
Yeah, great. That's fine. Sounds good.
All right.
Okay.
Well, thanks, Tish. I hope you have a great Sunday afternoon. And
some birthday parties to go to.
Yeah, well, I hope Pascal has a great time.
No worries.
All right. Thanks.
See ya.
See ya. Okay. So Tish had some other obligations which he had to get to, so he couldn't hang around for the entire 2 hours. But that was really interesting. Energy monitoring is something that I've played around with a little bit over the years. I've done, quite a few years ago, I worked on a commercial energy monitoring project, which I've mentioned on previous live streams. But we were doing that using very, very crude technology. It was using, actually, way back then, it'd be more than 10 years ago. It'd be around 10 years ago. We were using the equivalent of an Arduino Uno with some current transformers, and we were doing very low speed sampling. So it certainly wasn't doing anything like the work that that Tish can do using these ASICs that are designed specifically for energy monitoring, and it can do potentially thousands of samples per second. So if you think about the shape of an AC power source, the voltage that we talk about, like if we talk about mains voltage being 240 volts, that is the RMS voltage, so root mean square. So basically you can think of it as being, if you think of the waveform being a sine wave, and here I'm going to do my stupid diagrams with my hands thing again, which doesn't really help all that much. So what we're talking about is not a constant voltage. 240 volts AC is not constantly 240 volts. It is going through a sine wave at a frequency dependent on the electricity supplier. So it could be 50 hertz or 60 hertz in Australia. Yeah, it's depending on whether you're in Australia or the US or whatever. And so if you take an instantaneous voltage measurement on an AC voltage, what you're looking at is the voltage at that particular part of the sine wave. And by using ASICs, like Tish is doing in these devices, you can measure the voltage at, you can do it very, very quickly, and you can see what is the current, what is the voltage at this particular part of the waveform. And by doing that thousands of times per second, you can build a much more accurate picture of what is going on with the power, rather than just the very crude sorts of measurements that you can do with, say, taking a CT and then passing it into an AVR and then sampling it at a relatively low frequency. So I've seen Tish's hardware in the past. He came along and did a talk at the Open Hardware Miniconf on the Gold Coast in January this year, and that was very interesting. But what he was talking about there was his project. He's actually done more projects than I was aware of. I think, like many people, once you get into this sort of space, you start with a particular idea. You want to build one thing, and then before you know it, you've done 10 different things, and they may all be related to each other. So in his case, he's built, as you can see, the DIN rail mounted board, which has the power supply on it, and various and the riser, so you can plug different interface devices onto different ASICs and different processors. But he's also done other projects that are related to it, like other DIN rail mounted devices. So certainly some interesting stuff, and I would really like to play around with that sometime. Now, I know that one of the topics that comes up on the Discord quite often is energy monitoring, and I am really surprised that I don't already have a topic for it. I thought there possibly was. Maybe, I don't know. I thought there was one there. So I think what we should do is make an energy monitoring topic on the Discord, and then anybody that wants to chat about this sort of stuff, come along and ask questions, show your projects or whatever. I'm just looking around now because Tisha talked about the Kogan energy monitors. Well, there are some in a box. I can actually see them from here, but I won't go and grab them. I've got some of the little Kogan energy monitoring devices, which they look a little bit like a Sonoff S26. So it's a plug pack that you plug into a wall socket, and then it gives you a power outlet, and you can control the load, so you can turn it on and off. You can also flash them with Tasmoda, which is what I've done, and then it can report the voltage and the current and the power calculation for whatever you are powering through that device. And as I was saying to Tish, I found that the output from it is quite inaccurate, and as he said, that could be because of lack of calibration. But even that sort of thing is very useful in itself, because it means that you can, at the very least, tell whether a load is drawing power, to not necessarily you're talking about a few percent accuracy, but you're just talking about, yes, it's drawing hundreds of watts, or no, it's drawing a couple of watts. And that can be very useful for things like notifications on appliances in particular. So one project that I have not talked about on any live stream, I haven't shown it on a video yet, is something that's actually fairly common to do. What I've got is a Sonoff Power, I think it's the 16 amp version, I can't remember. So I've got a Sonoff Power that is connected to the clothes dryer in our laundry, and when and that allows me to tell when the clothes dryer is running, and then you can send a notification when it finishes, because you can see that the power usage has gone up. It's been running at like 2000 watts or whatever a clothes dryer takes. They really suck down the power, and then when it turns off, it drops pretty much to zero. So you can see at a gross level whether an appliance is drawing power or not, and then you can do things based on it. Oh, James just asked, can we also have a pets topic and we can post pictures of our pets? Sure, you can do that. There should probably just be a general off-topic. I think there is a general off-topic channel somewhere in the Discord. I'm not going to go looking for it right now. Aaron said he definitely thinks that power line data for IoT communications deserves a discussion and further exploration, maybe CAN type implementation. Yeah, so that question that I posed to Tish about communications within a switchboard, and his suggestion was Modbus. That is something that has been bugging me for a really, really long time, like years. Right from the early days of when I started messing around with my DIY home automation system. And one of the early things that I did was go and visit a demo house that used to exist. I don't think it exists anymore, but many years ago, Clipsal had a demo house down in Clifton Hill where they had a warehouse or a factory space. And then they had a builder come in and build a partial replica of a house inside the factory, which was really weird. What you would do is walk in. So this is the same facility they used for warehousing and training and things. So you're going to the factory area, and there was a training room with, the whiteboard and projector and all the desks and things where they would teach electricians how to install C-bus devices. There was a warehouse area where there were just racks and racks of products ready to ship out to retailers. But in the warehouse was a house, which was really weird because there was a frontage with a veranda and windows and the front door, and there was the roof, like a ColourBond roof, but the whole house was inside a warehouse. And it had been built from scratch as a demo environment where they could show their automation products and use it partly as a teaching tool as well, so that electricians could come along and see this fake house inside a warehouse. So I went along to that particular installation. I can't even remember how I ended up getting in there, but my wife and I ended up, I think I just called them and said, can I come and visit you? And they said, sure, come and have a look. So I got to wander around inside this demo house. And the way, I know I'm chasing a squirrel right now. It's just because this is a cool thing. I wonder if there are any photos around. It would be really cool to post photos of this particular fake house inside a warehouse. So it was complete to the extent that you would walk to the front door and there was like a doorbell, and open the door and you go into the passage, and then there's a bedroom with electric blinds, and there was an electric cover on the skylight as well, so that what your home automation system could do is open the skylight in the morning to allow natural light to come in, so you could have it dark at night or dark when you wanted to sleep, and then have it bring up natural light. And because this fake house was inside a warehouse, they'd mounted some lights above the skylight to simulate sunlight. And that's actually how I got in touch with, how I ended up meeting my friend Darren, who runs Burke Automation, the company that does electric blinds and things, and it led to doing work on electric blinds with him. And that's because he had done all of the motorization in this demo house for Clipsal, setting up the electric blinds. And that was what I was really interested in. So I asked Clipsal about how their motorization was done, and they put me in touch with Darren. And we've been friends ever since. So I am so far off the topic now. The point of all of this was inside something like a Clipsal C-bus installation, you have multiple modules. So you have a DIN rail like this, and then there'll be a series of modules that are clipped onto it. Each of those modules might be something like an interface that connects to the light switches around the house, or it might be an output device which has relays in it to turn lights on and off, and then all of the lights in the house are wired back to the switchboard, or it could be a dimmer module, or it could be a power supply module which runs power to the other modules. So there are a whole lot of these different devices that you can plug onto the DIN rail switchboard and then link them together to build the system that you want to suit your particular house. And that was really what it got me. Oh, interesting. It contains field trip. Sorry, I just saw something in the chat. So the issue is, how do you build modular devices and link them together so that you could have, for example, a series of energy monitoring devices within your switchboard, or a series of switchable outputs in your switchboard, and be able to send commands to them. And I understand the use of Wi-Fi for this, because basically it makes things easy from an installation point of view, but it really doesn't strike me as optimal in terms of a permanent installation for reliability and everything else. If you've got a series of modules that are all physically like touching each other, they're clipped into a switchboard and they're in a row within 300 or 400 millimeters of space, it seems crazy to me that those devices need to use Wi-Fi connecting back out to an access point and then back to each other in order to be able to communicate. It should be possible to link them together and have some form of communication between them. So the way I have done that in my own switchboard at the moment is for things like the output relays. I have a controller which is physically mounted just outside the switchboard, and that provides switched outputs that can control the relays. So the relays themselves are mains rated and DIN rail mounted, and they are fitted inside the switchboard by my electrician. And then the control wires come in. The control wires themselves have to be mains rated as well, of course, because they're inside the mains environment. And so what I'm doing is directly controlling those relays using essentially, well, you can think of it as being two wires. So a ground wire and a 12-volt wire that switches the relay. But if we had something like a control module that could go inside a switchboard, something equivalent to a Sonoff 4-channel Pro or a Shelly Pro, then it would be really nice if we didn't have to rely on Wi-Fi for those to work. Now, one of the issues as well is that in a lot of domestic switchboards, the switchboard is probably just a little plastic box, and they're typically about this big. They're not really all that big. It's a plastic container with a single piece of DIN rail in it, and then there's just like a plastic cover that closes down over the front. So there's no real problem in terms of Wi-Fi coverage. But once you step up to more of an industrial sort of installation, something like, well, any kind of a big commercial switchboard installation, the switchboard isn't just a little plastic box, it's a big steel container. And that is going to kill Wi-Fi signal. So both of the, well, I have 3 switchboards in my house. There is the main switchboard that comes in, and then that distributes out to 2 subboards that are inside the house. And both of those are very large steel boxes. They're the sort of switchboard you would normally find in like a factory or some large commercial installation. And so trying to put Wi-Fi devices physically inside those switchboards is not going to be any good unless there's an access point right next to it somewhere. So I would love to get other people's opinions on methods of communication. And so far, things that have been mentioned are things like CAN bus, which is really interesting as well. CAN is both interesting and frustrating, and also Modbus So I've got to admit, I've got no experience with Modbus whatsoever. I vaguely know what it is, but I've never used it in any of my own projects. I don't have any personal experience with it, so it's something that I really need to investigate. And I do know that, as Tish mentioned, it's very common on things like solar inverters. So if you install a solar system, then there's probably a Modbus interface on the inverter for monitoring and control and different things. So I need to investigate that more. What I've kind of had in mind was maybe something like an RS485 sort of daisy chain serial bus, and I think Modbus is basically that. It's this is totally showing my ignorance here. I have never looked at the specs of what Modbus actually is. My vague knowledge of it is that it's probably like a daisy chained serial bus, but I don't know any more than that, and I need to check into it. So James said some industrial controllers and PLCs use a bus system with contacts between each DIN rail unit. When you plug the module next into it, it is electrically connected to its neighbors. That would be the ideal situation, because then you don't even need that little jumper around it. If you had matching connectors on the sides of the modules, you just clip them together. Now that could make it difficult in terms of being able to mount them onto the DIN rail individually, because you would need to clip them together and then take the assembly and clip them onto the DIN rail. But it's not like that's a really common thing anyway. You're not always installing and removing modules. They're typically installed once, they are wired up, and then they just stay there. So having some kind of a connector that links them together would be cool. If there are standards around that, that would be even better, but I bet they're not. I bet they are very specific to the manufacturers. They come up with their own ideas of how to do it, and so each one is different. Sion said, why can't they do ad hoc Wi-Fi, point-to-point, talk to each other? Yes, they could. So the devices within the switchboard can talk to each other using Wi-Fi, but it still irks me. The idea of using wireless to link two devices that are physically touching each other. There are two boxes jammed together in a switchboard, and you've got connections on them right there. There should be a simple way to take a little jumper cable and plug the two things together and have wire level communication with no interference problems, no bandwidth degradation problems, no security problems. And what can be simpler than a bit of wire with a connector on each end? That's just the way I think about it. Maybe I'm being a bit silly about that, and I should just use something like Wi-Fi. But it also just adds complication, like in terms of security. So, okay, maybe I'm chasing something that doesn't need chasing. But I think Modbus could definitely be worth investigating. So, what other questions do we have? TP-Link had HS110 power monitoring too. Any ideas about the accuracy of this? Was a question from John Clark. No, I don't know of that particular device. I haven't used any TP-Link power monitoring devices, so I can't answer that one. Now, I know that there are a bunch of questions that have been hanging around from previous live streams that I haven't got to yet. And there are some more questions, I think, in the Patreon section on Discord. But for this particular live stream, given that we've had Tish on for most of it talking about energy monitoring, I really want to try to keep to that topic if I can, rather than going off onto some totally unrelated thing. So, okay. So there are some questions in here, like Adam asked a question about MQTT topic structure, and I don't want to get into that right now because it is getting a little bit off topic of energy monitoring. So, do we have any more questions related to energy monitoring? Or one thing that I would really like to hear is whether people are more interested in monitoring at the end point, like at the appliance level or at the power point, or central, so within the switchboard. And I have a feeling that most people that work in energy monitoring focus on the switchboard side of things, as Tish has been doing, and most consumers think about it from the point of view of replacing power points and monitoring at the actual point of the load. And so what I see, which I think is a little bit of a disconnect, and I know there are people that have experimented with building their own versions of something similar to what Tish has done, but built into a PowerPoint, and you can get energy monitoring PowerPoints now. In fact, I have one sitting in a box just back there, ready to connect and test. I haven't plugged it in and tested it yet, but that will be coming soon, I hope. Also, I should apologize that my regular scheduled videos are not so regular and scheduled. I've been derailed recently. My last actual proper edited video, I think, was in March last year. No, not March last year, March this year. So it's been a very long time since I've done a video and uploaded it. So I really need to finish off the next one. I've got a couple of videos that I've been working on for a very long time, and I'm just having trouble finishing them for whatever reason. Right, so Zivik said, I'd be happy to have a single total current usage and individual monitors just on devices I've put at the point of controlling and usage, i.e. light switches. I think that really summarizes it for me as well. My situation is a little bit different because of the way my house has been wired, with all of the loads wired back to the central point. But in a typical house environment where you have a small switchboard and you have maybe 3 or 4 power circuits in a typical house, and you might have 1 or 2 lighting circuits, having an overall power usage for the house is very useful. And then for specific appliances, having monitoring just on those appliances gives you a little bit more insight. For devices that might be turned on or off occasionally, or you want to understand a little bit more about how that specific device is using power compared to the rest of the house. So yeah, I think that is the ideal model for most people. So Doug said, I think the DIY folk, when measuring total usage at the board, can tell individual device usage from real-time graphs. That is usually the case, yes. It's one, when you start monitoring overall usage on a house, many of the devices that you care about will be using power that is in the many watts region. It's not going to be something that's using 100 milliwatts or some tiny amount like that. It's going to be devices that are using 20 watts or 30 watts or hundreds of watts or maybe even thousands of watts in the case of something like a clothes dryer. And if you are measuring the overall power usage of the house with a reasonable degree of accuracy, you will see that it's very stepped. It's not like a curve that sort of moves around. It moves in fairly discrete increments, and it becomes, once you've started looking at it for a while, it becomes reasonably easy to identify when devices have been turned on or off. And obviously the total is going to be cumulative. It is the sum of all of the devices that you have in your house that are turned on at the moment. But if your house is currently running at a certain power level, and then a device is turned on or off, you will see the step. And so you can, just from you using your human brain and looking at the chart, you can often identify different things. Like you can say, oh, look, the coffee machine has just been turned on, or whatever it happens to be, because you know the increment that happens. Oh, Mike Conti said, or load shedding. So load shedding, or another way of looking at it is moving loads, is a very interesting thing to look at. Now, there was a blog post just recently. I can't remember who put it up. It might have been Tablatronics or someone. Or was it Decryption? I think it might have been Decryption. Did a blog post about switching over to the Amber power provider earlier this year, and then looking at the effect of that. So when you sign up with a power company, they will typically give you a rate which is a certain number of cents per kilowatt hour for the energy that you use. And it might be 22 cents per kilowatt hour, or whatever the number. And that number applies across the entire billing period. But the thing is that energy usage, if you look at it in the aggregate across a city, is very time dependent. There will be periods where the usage is very low. For example, early in the morning. So during the night, when most things are turned off, there's not much lighting, there's not much aircon running, all of those sorts of high energy usages are turned off. And then you have very high peaks, which might be across very narrow bands. And part of the way, in Australia at least, that is dealt with is that the tariffs that are charged for power vary depending on the time of day. So the energy retailer that you sign up with will charge you a flat rate of, say, 22 cents per kilowatt hour. But at some time of the day, they might be being charged 4 cents a kilowatt hour. And another part of the day, they might be being charged 40 cents a kilowatt hour. So their cost varies during the day, even though what they are charging you is a flat rate. And their flat rate is calculated so that it will average out across their varying costs, and they will still make money on you. But it's a little bit of a statistical gamble that they are making. So the interesting thing about, I think it's called Amber, so this other energy company in Australia, is that they are an energy retailer, but they don't just charge that fixed rate, which is based on the statistical average plus profit margin. They charge based on the rate at the time in fairly narrow increments. So if you use power in the early hours of the morning when it's cheap, you don't get charged as much as if you use it at 6 p.m. on a Friday when everybody's got home and turned all their devices on and that sort of thing. So yeah, spot prices, as Andrew said. Mike O'Connor pointed out Amber and Power Club. So there are probably several retailers like this now that are taking the cost prices from the wholesaler and then doing their retail billing based on those prices. So the reason I bring all of this up is that this is really powerful if you have the ability to move your loads into lower tariff periods. And you can only do that if you know two things. Firstly, you need to know what is using power in your house and how much it's using. And secondly, you need to know when those low tariff periods are. So if you're with a retailer that will charge you based on the current spot pricing from the energy wholesaler, and you have some visibility of what that is, and ideally you want predictability. So you want to be able to see over time, oh, look, this particular period of time is generally when the price is cheapest. Then if you are monitoring power usage within your house, and you know that when you run your dishwasher, as a classic example. So a dishwasher, you can typically load, and then you can leave it loaded, ready to go for a period of time without anything bad happening. Now, if you've got clothes that you have washed and they're wet, and you put them into the clothes dryer, but then you leave them sitting in the clothes dryer for 12 hours or something, they're going to be sitting there wet. That's not good, because the clothes can go moldy and you can have bad effects. But something like a dishwasher, you can load it, and if you can schedule your dishwasher to run at 2 o'clock in the morning or at some time when the spot pricing is really low, that can end up saving you a significant amount of money over the course of a year. So being able to do things like load shifting into low tariff periods, combined with energy retailers that give you the option of spot pricing, is very interesting as well. And that's also an area where automation can be really useful. If you've got some kind of a device that is tied into your home automation system, then you can set rules for it. And in the blog post that I was referring to, and I wish I could remember who did it, I think it was Decryption, the example was having an electric car that is plugged in and it's charging, and you can start to build some really interesting logic around it. So if you can imagine, you've got an electric car, you've got a solar system, so you're generating your own power, you've got battery storage within the house, and you've got connection to the grid. And then you've got future events like usage of your car. So imagine a system where your home automation system has insight into all of these data sources, and it sees that on your calendar you have a trip scheduled and you're going to need to drive a long distance tomorrow. So you need your car to be fully charged. And the tariff price on the grid power is going to be extremely low between a certain period, then it could use that to fully charge the car in that period at the lowest possible price. But if it sees on your calendar that you're not going anywhere tomorrow and your car already has, say, 60% charge on it, and there is not going to be any particular cheap pricing within the next 12-hour period, then don't charge the car, because you can just leave it sitting at the 60% and then charge it when the next cheap pricing comes around. And there are lots of little optimizations like that you can do once you have access to that data and have control over the different elements of the system. So lots of cool things you can do there. So some questions that have come in while I've been just randomly chasing squirrels. So Unexpected Maker. So Sion said, any idea how energy meters deal with earth leakage? Can they detect and compensate for it? And that is something I don't know. That is interesting. So James said that his energy monitor only has 2 CTs here in the US, one on each phase, and I don't have one on the neutral. I would need that additional one to see a delta. Yeah, so earth leakage. And the thing is that earth leakage is typically incredibly small. So RCDs, or residual current devices, are designed to trip when the delta between the neutral and the earth is, I can't remember the number, but it's really small. It's like down in the milliamps region. And being able to measure a few milliamps of power on an energy monitoring system, it's not really what they're designed for. They don't go down to that level of accuracy at a very low level. So Frank said you can read the leakage current of a circuit by using a clamp meter across active and neutral. Yeah, you can. I've never tried to do that. So my expectation is that what you would be measuring there is so small that you would have trouble picking it up. And RCDs are designed specifically to pick up that tiny amount of leakage. But if you just have a current clamp on active and a current clamp on neutral, and you're trying to detect the leakage through it that way, I don't even know if you could do it. But Frank, if you have done something like that, I would love to know that. Being able to measure that sort of thing would be cool. Okay, so Oh, Sion said 10 to 15 milliamps, I think. Yeah, that's the level at which an RCD will trip. And Frank says, I use a clamp meter which has a 200 milliamp scale to test. That is very accurate. That's interesting. Okay, cool. So perhaps you can do that. I wouldn't have even bothered trying to do that because I would just assume that you're, they're trying to measure that leakage with just clamps. Wouldn't be accurate enough. Very interesting to see. So I am going to wrap up the live stream in a second, but before I go, I just want to encourage you to check out two things. Firstly, after I finish this live stream, what I'm going to do is edit the description and add the links to Watnik and also to Tisham's GitHub profile, because he's done lots of interesting projects. And the Watnik site, so Watnik is basically like his blog as well, and it's got other things on it that aren't directly related to energy monitoring. Like at the moment, I think the top story is about a containerization thing, which is more, something related to his infrastructure work and his SRE work, but interesting nonetheless. And I'm also going to make a channel in Discord specifically for energy monitoring, and I am amazed that we don't have one already, because we should. This is a topic that I think needs a lot more focus, because there are so many people that are interested in it. So unless there are any last minute questions, I'm going to wrap up this stream. And okay, one quick thing I will follow up with. John Clark said, I'm off-grid, so apart from being able to detect and control devices going rogue, we need to be able to answer questions such as, do we have enough power to get through the day and night? That is a really cool sort of use case. So being off-grid means you're totally disconnected from the normal electricity grid, and you have to be entirely self-contained, which means you have to be able to generate the power locally, and you have to be able to store it locally, typically using a battery system. And that might be, it's often referred to as a RAPS, I think it is, Remote Access Power System, something like that. Remote Area Power System, I think that's the industry terminology. And so if you have a certain amount of battery capacity and the day is it's starting to get a little bit late in the day, the sun is going down, the output from your solar is decreasing, and your charge level is at a certain point, you kind of need to know whether you are going to make it through until you can start recharging. So managing that resource becomes really, really quite important. And having insight into how much power you are currently using is critical. You really need to know that if you are running all your current appliances and your batteries are going to be flat by midnight, then you've got a problem. It's a little bit like being on a road trip and you're managing the fuel in your car. You know how far you can go on your current level of fuel consumption, and are you going to make it to the next petrol station or not? So thank you everyone for coming along, and you can't see this, but a big thanks to Tish for being part of this live stream as well. It's really cool having guests on. I like it. I'm going to do it more. So we will definitely have some more guests in the future. And now, because I'm running this out of StreamYard instead of OBS, I've got to look at what I'm doing and figure out how to end the live stream. All right, I think this is it. Thank you very much, and have a great weekend, and I will see you all soon. Bye.